Okay, Assalamualaikum and I hope everybody have a good day. So today we're going to continue with chapter 5. So basically chapter 5 is about um, partial differential equation. Some of the method inside this chapter you have already learned in the previous chapters. So basically in this chapter it is more on the application, okay? So what is partial differential equation, or the short form is PDE, is when you have a equation, let's say the equation is u which is equal to uxy, means in u it has a variables of x and y, and x and y is an independent variable. So a PDE is an equation containing at least one partial derivative of u, means we differentiate the equation u at least one time to x or to y. Okay, so the notation is written as, if u is the original equation, if you differentiate with respect to x, you will write it as ux, which is equal to delta u delta x. So for partial derivative, we didn't write it as du dx, but we write it as delta u delta x. So if let's say they give you uxx, means they differentiate with respect to x 2 times. So you will have delta u, delta square u over delta x square. If they write it as uy, means they differentiate with respect to y. And if they write it as uxy, means it is delta square u over delta y delta x, or you can also write it in a separate form like this. So partial derivative, we have few example. It is applied in dimensional wave equation, dimensional heat equation, dimensional Laplace equation, dimensional wave equation, dimensional heat equation. So as you can see, all of it, if let's say they write it as delta u delta t, means actually it is came from delta, you have actually from the original equation, they differentiate it with respect to x for 2 times, something like that. Okay, so the first method in PDE is method of separation of variables. So this method is actually very simple, and I think we have learned about this method in chapter 2 or 3. Okay, so let's consider heat equation that they just gave you in the above section. So let's say we have delta u over delta t is equal to k square delta square u over delta x square. So the aim is always to find the solution for u, where u is a function that depends on x and t. So basically, we are trying to solve this partial derivative to get the original equation, which is in u form. Okay, this is basically the general idea of this subject, right? Differential equation. You are trying to solve differentiation. Okay, so in order to solve this equation, so they use a method of separation variable. So the general solution will be like this: uxt is equal to xxtt. Means we say that if the equation is uxt, so the general equation should be a combination of variable of x and t. Although we don't know what is the exact equation, but we can say generally the equation must be in the form of x and t. Okay, so x is some function of x and t is some function of t. It's correct, right? Because you write the equation as uxt. So basically you must have x and t inside it. So By separating the variable x and t, we reduce the problem of solving the PDE to solving the two ODEs. So if we can solve what is x and what is t, basically we will have the original differential equation. So how it works? Assume that PDE have the following solution. Okay, we say that the general solution is like this. And then we look back at the original equation. First, they differentiate with respect to t and also with respect to x squared. So they differentiate one time with respect to t means the general equation will be xx t prime t. Means we have, in this case, we already differentiate t one time. And in the equation also, this one, we differentiate with respect to x two times. Means if this is the general equation, we write it as uxx equal to x double prime x tt, right? So basically, from this equation here, we will substitute into this equation here, heat equation here, okay? So just substitute this in the form of xxtt just now. So it become xt prime equal to k squared x double prime t, right? So and then we rearrange this equation into this form. How to rearrange? Okay, we have two variables which is x and t. So you put x at one side, t at one side, okay? And then the above of the fraction must be the variable that has been differentiated. So in this case, actually this x is bring to this side and this t is bring to this side, and the variable, the constant inside the equation must be with the variable of other than x. So in this case, we have other variable than x is t, so k will be here at this side, okay? So remember, the variable with differentiation must be at the above part. So this one will be at this side, so it becomes x double prime over x. But we rearrange, we must put x at the left hand side. So t will be at this side, so it becomes t prime over t multiply with 1 over k square. You guys can try to write this form and try to write it in this form, so that you will understand more of how they rearrange this equation here. Okay? And then, since a function of t can equal to a function of x only when both functions are constant, so we say that this equation is actually equal to lambda. So lambda is actually a constant. Okay? So when you have this condition, you can write this equation here as two separate equation, ordinary differential equation. Okay, sorry, ODE is ordinary differential equation. Okay, so this one, if you can see, they only take this x double prime over x equal to lambda. So and then they bring this x to this side and bring back this to this side, you will get this. And for this one, 1 over k square t prime over t is equal to lambda. So when they rearrange, they will get this equation. Okay? So now, the problem of solving one partial differential equation, the heat equation just now, is now reduced to solving the two ODEs. So basically, this is easier to solve because do you guys still remember when the last time I told you, when we have two variables that we need to know what is the value, we must have at least two equations. So now we have two variables, which is x and t, and we have two equations. So that means you can solve it. Okay.